Hello, everybody. So today we're going to finally introduce some quantum mechanics to help solve one of the classic problems of 1900. So as we encountered last time, a black body is a solid object that essentially has a series of resonant vibrations of electromagnetic radiation that will slowly release radiation, which can be measured. So what we ran into is a slight problem when you try and solve this problem with classical physics. Because what you want to try and figure out is how is the spectral energy density, or how much energy is contained in each one of those vibrational frequencies. Well, classical physics predicted that every wavelength had a similar energy of 1/2 kT. When we did this, it gave us a spectral density, which had a inverse relationship with wavelength, which meant that we had the ultraviolet catastrophe, and at low wavelengths, we ended up with infinite energy density, which just wasn't possible. So this was essentially corrected in early 1900 by Max Planck in one of the most reluctant discoveries of all times. And what he said is that, well, most of the problem comes from this low frequency region. So it should be fairly clear that energy has some sort of dependency upon the frequency of light, which seems logical now, but at the time was very new and quite provocative. And in fact, Max Planck hated this idea so much that he kept on going to other people to find any other possible solution that would give the right answer. But what he came upon is the idea that energy should be proportionally constant with the vibrational frequency of the light of question. So essentially, we see a direct relationship in between vibrational frequency and energy of the light, modified by two key constants. One is what we now know as the Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds. And the second one is a random integer value. So this essentially is going to be related to the number of molecules that are in the ground state versus in, say, the first excited state, which can release this energy. And this introduced an idea that's quite comfortable to us now, but was very provocative. There are such a thing as energy levels. So what it really is showing us is that only certain vibrational frequencies are going to be allowable. And that each one of these vibrational frequencies has given energy levels. So you are releasing this energy as discrete packets, and the shorter the longer the higher the frequency, the smaller the wavelength, the higher the energy. So while I can fit in a lot of small wavelength vibrations, it turns out that each one of these has a very high energy. And this was quite provocative at the time. And again, this also shows that with this n value, that light is divided into discrete quantized packets. So this quantization of light and quantization of energy is the quant in quantum mechanics. So what we're dealing with is mechanics that, unlike classical mechanics, where everything exists on a continuum, now we have to deal with the fact that energy and movement is actually quantized. And if I've got a low frequency or high frequency, this means I have a low wavelength. And this also means that I have a very high energy state. And because I'm required to go from a low energy to a high energy, this means that this excitation is much less likely to occur. So this is the reason why we see a lot less of high frequency or low wavelength light, is because it's very hard to make this energy jump. And so what we can do is we can take this equation for energy by Planck and feed it into a Boltzmann distribution. So if you were in PChem 1, you may be familiar with this idea. Otherwise, the basic concept is the probability of finding a system in a given state say the first excited state, is going to be related to the exponential of the energy of that state divided by the Boltzmann constant and the temperature of the system. So thus at high temperatures, I am much more likely to occupy an excited energy state. However, because all of my probabilities have to add up to 1, we include the partition function, which is essentially the sum of all of the relevant probabilities. So the probability it ends up in any given state. This means that the probability of an excitation is simply going to be given by the exponential of the gap in between these energy states, and then essentially just adding up all of the possible energy states. So using some mathematical tricks, and again, integrating over full 3 dimensions, what we find is that it's possible to generate the Planck distribution for spectral density. So this is again our same spectral density, so the energy contained in light of wavelength lambda and temperature T. And again, we still see the same, we have a energy value of 8 pi hc on top. Now the numerator is where the real action is going on. So we break it up into 2 terms, which is first a polynomial term of wavelength to the 5th, and the second is a dampened exponential term. And what this ends up doing is giving us our original experimental energy density distribution, where at very short wavelengths, we have no, our spectral density is 0, and at very long wavelengths, we see this tail, and we have a peak and an intermediate density. And we can really kind of illustrate what's happening by looking at some of our limiting cases. So this is a classic physical chemistry trick. If you don't know what's going on, try and examine your limiting cases. So the first one is going to be short wavelengths. So in the classical distribution, this went to infinity. Let's see what happens with the Planck distribution. So first, what you may notice is that as the wavelength goes to 0, we'd expect this polynomial term to also go to 0. We're dividing by 0. This is a, well, let's be honest, a very, very bad thing. But we also have this exponential term. And as wavelength goes to 0, so this term goes to 0, this means that my exponential essentially starts going to infinity. And what ends up happening is that my exponential is going to go to infinity faster than my polynomial term approaches 0, which means that I can approximate this whole bottom term as infinity. So anything divided by infinity should essentially give a value of 0. So what we tend to see is that at short wavelengths, so small lambdas, my whole spectral density should go to 0. And congratulations, this is what we predict, and it avoids the classical physics problem of the ultraviolet catastrophe. But let's also think about what this physically means. What we see here is that as my wavelength goes to 0, what I have is a lot more energy in my system, because low wavelength light, huge energies. But the problem is that what this exponential term demonstrates is that under these high wavelengths, I'm very unlikely to get there. So it's going to be very hard to obtain these high wavelength lights. And this is what essentially dampens our function. So while I have a lot of energy whenever I do release a photon down here, I'm very unlikely to make a huge energy leap at most temperatures. High enough temperature, and sure, you can make this work, but you'll never really get much production in the ultraviolet region. Now let's go ahead and take a look at the other region. So this is the region that classical physics actually succeeded in. So Rayleigh-Jeans was pretty good in this area, and let's see if we can go ahead and replicate the results. So for long wavelengths, lambda goes to infinity. Now what we can do is we can treat my exponential function with a power expansion. We're going to truncate it after the first term. So what we have here is 1 plus hc over lambda kt. So essentially what you're doing is you're pulling the exponential down, and it's 1 plus that. Now when we do this, well, we get a 1 plus, and then we get a minus 1. So these ones just end up canceling out. And what I'm left with is, well, I'm going to have some HCs that will cancel out. I'll have a single lambda term that cancels out. And all I'm going to be left with is 8 pi kt over lambda to the fourth. And lo and behold, this should look fairly familiar, as this long wavelength spectral density is the same answer we got for Rayleigh genes. So this was the part that classical physics actually got right. So what this means that what Planck distributions does is it essentially gets us the classical answers at long wavelengths while giving us a value that goes to 0 at short wavelengths. So likely what this means is that if I'm good at the two ends, I'm also good at the middle. And so the Planck distribution, in addition to doing good at long and short wavelengths, should also give us a lot of information about intermediate wavelengths. And one of the reasons why this is actually really important to have is it turns out that being able to determine, say, the spectral density at these intermediate wavelengths is usually one of the tools we make use of in order to determine, say, the temperature of distant stars. Because if you're able to measure a spectral density coming off of a star, well, you can just simply figure out what temperature will give you that result. So Planck distribution was actually a huge boon to astronomical discoveries as well. But we also want to make sure that it can generate our two classic distributions. First of all, we really want to make sure it can nail Wien's law. And as a reminder, Wien's law was the correct prediction of the maximum wavelength. So this is essentially the peak wavelength at those intermediate energies. And so what we can do is we can actually try and determine the most likely wavelength, so this lambda max, by simply taking the first derivative of the energy density with respect to wavelength. So take this, set it equal to 0. I should be able to find the most probable or maximum value. Now, because this is a PChem class and not a calc class, we'll go ahead and jump over this derivative. But trust me that what this ends up essentially producing is a value of HC over 5K. So you can start to see where the HC comes in. 5 comes from my lambda term, and then of course K's along for the ride here. Now it turns out that HC over 5K is actually the exact constant empirically predicted by Wien's law. And in fact, this is since Boltzmann's constant was already known, this was one of the first ways in which Planck's constant was determined. It's been validated in any number of ways afterwards, but this was very crucial in determining one of our fundamental constants. So we do have agreement with the Wien's law. This means that I can make accurate predictions of the maximum wavelength, which, as I said, is really important when making measurements of the temperature of stars and other solar systems. However, one of the other things we want to try and determine is the overall energy density, which again was the Stefan Boltzmann distribution. So we want to make sure that the Planck distribution gets us back to Stefan Boltzmann's law. So we can essentially do this by taking the integral of our spectral density over all of the wavelengths, making sure we have the right total energy. So we can go ahead and set up this integral. Yes, it is a little bit messy. So we'll go ahead and just jump straight to the answer. So it turns out that this gives us an answer of, well, let's say a lot of constants. We have pi, we have Boltzmann's, we have Planck's, we have the speed of light. But the real important feature here should be that we find that our energy density is dependent proportionally to temperature to the fourth power, because everything in here is just a series of constants. So we do actually get stuff in Boltzmann's law back, where we have a dependency on the temperature to the fourth power. But not just that, it turns out when you actually calculate the value of this huge mass of constants, it actually gets you the constant from stuff in Boltzmann's law. So yeah, this actually is exactly what you're looking at when you're founding a new branch of physics, is that by making a couple of key approximations, it doesn't just reproduce one or two of the findings, it reproduces all of the findings. And in this case, Planck's distribution, Planck's insight to light, no matter how reluctant he was to make it, was really important in solving all of the features of the behavior of a black body system. But what I want to focus on before we end is the sets of key lessons that we get from black body radiation. First of all, and this one is really important, is that light moves in quantized packets. We'll later develop this into the idea of photons. Second, and this one can't be understated or overstated, chemical systems have quantized energy levels. So this ends up eventually leading to the idea of atomic and molecular orbitals, which is going to be a major feature of this course. So the next bit, and this one is very important when using light to determine a system, is, as we almost started on day one, the energy of light is going to be proportional to the frequency of the light. Now, this is also one of the reasons why wave numbers is so common, because it's also, the energy of light is also going to be proportional to the wave numbers. You just have to add in an extra speed of light constant to essentially correct for your units. And again, then watch out, because we're typically producing wave numbers in centimeters and not meters. And finally, one of the biggest ones is how quantization of energy relates to the Boltzmann distribution. So what we find is that if energy levels are going to be quantized, this means that they're separated in how likely they are to occur. Low energy levels are going to be frequently occupied. High energy levels, very uncommonly occupied. And this is going to give us a way to describe how likely we are to find a molecule or an atom in a given state, as long as I know the structure of the system and the temperature of the system. This focus on the temperature is going to be much more a feature of statistical mechanics. So we're going to be focusing a lot more on this idea of energy levels, and I'll occasionally bring up the idea of temperature to indicate whether something is or is not likely to be occupied as we kind of work through the material. But one of the biggest things is that these first set of approximations are super useful in providing the building blocks for quantum mechanics. These are essentially going to be our first assumptions as we move forward. We're going to essentially round out these a little bit next time as we talk about how we can use quantum mechanics to essentially correct for a couple other failings of classical physics. Until then, take care.